Turbulence in Neutron. And we'll do introductions after this talk.
Yeah, so for those of you that don't know me, I'll be introduced after the talk. Okay. So it's great to be here again. I recognized when I looked at my passport, it was almost exactly a year ago we had the Neutron Star continuous wave meeting, from which I can't remember anything, but must have been good. I also recognize today is April Fool's Day, so maybe this talk will be just perfect. I also recognize that Bryn gave this talk last week, so the only thing I've really changed from Bryn's talk is the first slide. I put my name on it instead of his. And so for those of you that were here last week, you can go back to sleep or something. But seriously, when I started preparing this, I was thinking, shall I add loads of new things that I don't really have to tell on? And I decided not to do that. And so, because it's Monday, and this is the first talk of the week, I thought it would be probably okay to go over some of the main basic issues. I'm going to do that from the point of view of a neutron star physicist, so someone that's interested in neutron star physics, and then I want to try to connect with the quantum vortex dynamics and turbulence issues, but I'm going to be doing that very much from the sort of neutron star side. And so, as usual, that's because that's kind of my comfort zone, so it makes some sense. Okay. So I thought, because it's Monday, I should start by reminding you of what it is we're trying to do when we model neutron stars. So one thing we're trying to do is we're trying to pretend that we understand all of physics every now and then. We're trying to understand the gravity because neutron stars are interesting and important for gravitational waves, for example. We need to understand electromagnetism and how it works in these super dense systems. And that's not the trivial issue, given that we're expected to have superconducting phases and so on. We need to understand the electromagnetism because it's worthwhile keeping in mind, for those of you that don't follow this every day, that it's been 50 years of pulsars, but we don't really know how the pulsar mechanism works. And that's a big, big tick. We certainly don't know why magnetars flare in giant flares, emitting gamma rays and so on, at least not in detail. We need to understand the interior, so we need the strong interaction, which tells us what the composition is and so on. We need the weak interaction because that's what dictates how the star evolves. And so that's the mission statement, the usual one for an astrophysics type audience. And then if you're kind of a little bit of a gravity person, you will emphasize that all this has to be done in general relativity or some alternative to that theory, because otherwise it doesn't make any sense to put in a realistic equation of state. You get things like mass, and for a given mass, you get the radius completely wrong, and so on. So these things are important. It's important to do them in a full sort of relativistic theory of gravity. But for this purpose, for the purpose of this meeting, the key point is that neutron stars are cold, and that means, from a low temperature physics point of view, that they should be either solid or superfluid / superconducting. And of course, we know, or we think we know, that they are both. The outer layer, what we call the crust, is an elastic phase. The core of the star has superfluid phases. The neutrons become superfluid. The protons become superconducting, probably with a phase transition from type 2 superconductors with flux tubes to a type 1 with some more large-scale microscopic magnetic regions at some point. And the key trick is to... I'm pretty unstable too, so that's okay. And so what we'd like to do is figure out, from a first principles theory point of view, what are the relevant pairing gaps. And so this has been, people have been working on this since, the 1950s, essentially. The bottom line is that we think that the singlet pairing gaps for neutrons and protons are pretty much like in BCS theory, with some suppression factors, because you've got, protons. So the protons impacting on the pairing gap for the neutrons and vice versa. but in principle, those are fairly well understood. The triplet pairing for neutrons is much less understood, and it's still, I think, open to the suggestion that there might not be triplet pairing at all, but that's a discussion. From the astrophysics point of view, you can ask, what difference does it make? And so the phenomenology for neutron stars is quite complicated, but we think there are at least 3 situations where superfluidity, superconductivity will make a difference. One is in pulsar glitches, which I think Bryn talked a bit about. I'm just going to mention it. The idea being that the sudden spin-ups followed by long-term relaxation that we see in radio pulsar data could be explained by the transfer of angular momentum from the superfluid phase to the crust, essentially, which is where the magnetic field is anchored, so we'd see the motion of the crust. But it's fair to say that we don't really know how this works. We don't have any detailed models for how glitches proceed. And so I'm going to touch a little bit on that a little bit later. Another option is that neutron stars undergo free precession, which is essentially the idea that if you have some deformation in a rotating body, it won't rotate like that, it will wobble. And so if you think, connecting with a meeting we had last year on continuous wave sources, if you think that a neutron star has some deformations in it, then there's no reason why it should rotate along an axis. Actually, the generic motion should be a wobble motion. So you can argue, and similarly, if you think that these glitches are the transfer of angular momentum from certain parts in the star to the crust, if that transfer of angular momentum is not perfectly axisymmetric, then again, it should kick the star into wobbling motion. But that does not appear to be seen in observations. So the generic picture you might have is that the transfer of angular momentum, whatever it does, cannot possibly be symmetric if you think about how small the vortices are, or the sort of 100 Fermi compared to the 10 kilometers. So we take some small region over here, the vortices move. Why should the small region over there, 10 kilometers away, move at the same time exactly with the other one? It's not a little bit counterintuitive. But it suggests maybe we're looking for some global sort of phenomenon. Cooling, so we have some data for temperatures or upper limits of temperatures in neutron stars. The superfluid phases, because superfluidity suppresses the nuclear reactions and introduces new cooling mechanisms through pair breaking. In principle, one can try to use cooling data to probe superfluidity. It's quite tricky. There's the famous case of the Gremlin Cassiopeia A, where the discussion is still going as to whether there is a real-time cooling or not. I'm not going to go into that, that's the safest. And then finally, linking all these things, in a way, is the fact that we believe the neutron star magnetic field evolves. Now, clearly, the evolution depends on the interior physics. It depends if you have type 2 superconductor, it depends on the motion of the magnetic flux tubes, so the outward motion of the flux tubes. That links to the issues I'm going to talk about, the friction, vortex friction. So this is a very, very complicated problem. There has been quite a lot of work recently in the last 10, 15 years on magnetic field evolution from magnetars, where we think that the observations require the field to evolve on, say, thousands of years. Okay? And that story works out if you have a field that lives only in the star's crust. As soon as you couple in the star's core, the evolution is much, much slower than we need it to be. And nobody knows how to resolve that problem, unless the solution is that you come up with a scenario where the star is born with the field only in the outer region, and there's simply no field in the core. But I think that's a tricky thing to actually come up with. So, yeah.
I just want to add another point to that list. Cooling of accreting neutron stars. We've observed about 6 or 7 of them. And there's a fairly detailed theory of the cooling. And I would say that detailed cooling requires both solid and superfluid component in it.
That's right. That should be added here, because that's actually a stronger piece of evidence for superfluidity than the Cassay remnant, I think, now, because the data is much better. So the main point may be, if you're an experimentalist or a lab system helium, cold atom kind of theorist, these systems are similar to the lab systems if you take a little box of fluid, but they're very different in the sense that we have to connect the different phases. Okay? So let me just give you one pointer as to what that implies. For example, if you take a lab system, you can decide to be above or below a critical temperature. In a neutron star, there will always be a region where you're near the critical temperature. Imagine taking this sketch, draw horizontal across for whatever temperature, like that 29 is very high, but somewhere. There will always be a point where you're near the critical, where the gap is nearly zero. And that means there will always be regions where you have to worry about thermal excitation. And that means you have to be able to understand how you transition in a real object from one phase to another. And that points to, I'm sure Vanessa will talk about that tomorrow, but it points to thinking about what happens in, say, transitions between helium 3A and 3B and things like that. So these are the kind of systems that are quite hard to build in the lab. But that's something I think we need to worry about, and yet we very rarely worry about. So there's been very little work in neutron star modeling on what happens close to these transition regions, and I think that's probably a mistake, because these regions can be very important when we're talking about vortex friction and so on. So that's my thinking on that. So just about glitches, I thought it would be nice to show a glitch plot, because obviously I'm talking about superfluids, so I should show at least a picture. So here is the Xray Pulse 0537 that glitches very regularly every few hundred days. And so it's been observed with the RXT for a long time, until the RXT died or ceased to operate. And you can see it's a fairly regular yet irregular behavior. It's difficult to explain. I'm not going to go into what the details are, because I don't know. Even though I have done quite a lot of work on it, I still don't know. So let me talk about instead what it is we're trying to do from the neutron star point of view. Okay? And this is maybe the main message of the whole talk. First of all, we have to develop a theory for fluid dynamics. Right? We're talking about the 10-kilometer object with superfluid, superconducting phases and phase transition and whatnot, with vortices of the 100 Fermi scale, flux tubes similar and so on. But we've got too many vortices and flux tubes to be able to think about individual. We need to average, we need a fluid model for this system. Okay? And I think that logic has driven a lot of what has been done, and how we connect, traditionally have connected with the sort of low temperature physics work. So what is it we got? Well, this problem is quite different from what goes on in lab systems, because in the simplest case, already at the simplest case, we can think of at least 3 or 4 different components that we have to have. Simplest matter configuration with neutrons, protons, and electrons in the core. The electrons you can forget about, they never become superfluid or anything, but they have to be there for charge neutrality. So we have at least a charged fluid or gas of electrons. The neutrons become superfluid quite early on, at least in the outer regions. So we have a superfluid neutral phase. We've got the protons most likely superconducting, so we have a superconductor. And then in each of these phases, we've got vortices in the neutrons, because we know that neutron stars rotate. And we've got flux tubes, if there's a type 2, in the protons, because we know the star has a magnetic field. So we need to average over vortices and flux tubes, put them together with the proton condensate and the neutron condensate respectively, and then build some kind of fluid model.
What about the electrons? So they rotate like a rigid molecule.
So the usual story, which I think is just naive, okay, is that we're talking about rigid body rotation in general, right? And I'm going to come to why I think that is probably not right. I think in reality, we're not talking about rigid body motion at all. Superfluid neutron component,
Yep.
essentially with average vortices built in. So it's something that looks like a normal fluid, if you like, with vorticity, although the underlying theory is quantized vorticity. Right? I need the same for the protons. Right? So that's two. Then I need the electrons, which can flow relative to the protons because I know I need a charge current. And then I need an entropy component, by which I mean something that takes all the thermal excitations, neutrons and protons, as one. Okay, that's four. And then that
what about the electrons?
And the electrons I can ride with that one or not. So that's a minimal counting. Okay, the maximal counting would be much bigger than that. Because that's still assuming that we're in the neutron, proton, electron region. I could have muons, I could go deeper in, I can have hyperons and deconfined quarks and all sorts of mess, okay?
No, but those probably are small.
Well, but if you're thinking about where, these phases might also be slightly different from the sort of the fluid dynamics point of view. So I'm just trying to say that, like, when we model these systems in trying to build, say, models for glitches, we tend to build it based on the classic two-fluid model from helium, okay? Because that's what we could sort of understand how to do. But I think that that's not even, well, it might be good for giving us an intuitive picture of how things work, but it's not the actual starting point. The actual starting point has to be at least 4 or whatever counting you like, okay? But the counting I suggested does not really take the thermal excitations very seriously. So that might still be a problem.
So you think they could be neglected? You see the normal component could be neglected?
Well, I think that the answer is yes, unless you're close to the
entropy at the same time. So,
yes, that's right.
So how you do that?
I agree. So I think yes and no at the same time.
But your naive counting is just lumping all thermal things into one.
Yeah, and I would think that because that's the easiest, but it's not obvious that that's what happens. Okay, so I'm just saying that the usual story you would get is that we look at how things work. We look at things like the glitches. We need 2 components, and then we stop at 2. Okay, we don't. And if you look at people that develop the theory, the fluid dynamics theory, they also stop at 2. Okay, I'm just saying the minimum I want to do is to understand the bulk dynamics. Okay, for which I need the crust and the superfluid, so I need 2. Then I need the heat, so I need the heat flow, that's 3. Then I need the electromagnetism, I need charge currents, that's 4. That's the sort of physics, or the astrophysics down counting. And then you start from the smaller scale and you count up, just like we did. Then you can kind of reduce it to 4, but you cannot reduce it to fewer degrees of freedom than 4, okay? And for anyone that's done fluid dynamics in the two-fluid model, you know that's messy already. So this souped-up four-fluid dynamics is not a popular proposition. Okay? And then, of course, as a purist, you have to do it in general relativity, as I said. So that adds some complexity to it. But that's, you know, that's reality. So just live with it. Okay, so what's new and what's different? Okay, so the two-fluid model, I think we're using it because that's what the people did in the olden days. They took what was done for helium from the 1950s and just said, well, we need two components for the glitches, so let's have two components. But for us, the problem is a little bit different. As I said, we don't, when we count to two, the two does not include splitting between superfluid and normal components. It really involves only splitting neutrons from protons and saying, let's ignore the magnetic field, so we let the protons and electrons move together, there's no charge current. Let's ignore the heat, so let the entropy, whatever it is, the thermal excitations flow with the electrons and protons as well. Then we have all those guys and the neutrons, there's two. And then we smooth average over vortices so that the fluid dynamics looks a little bit like a normal order equation type fluid. Okay? But hidden underneath all of this, of course, these are the small scale physics and the averaging and how the averaging is done and so on. And that's something I think has never really been gone into too much detail. So here's my version of these equations. There's no, nothing particularly odd. I've just labeled each component however many you want with an X. Here I'm thinking neutrons and protons and so on. So the continuity equation for each. So this is the Newtonian version. A momentum for each, which I call P, with the usual convective derivative, a common gravitational potential, because gravity is an egalitarian thing that doesn't care about what makes up the mass and energy. A chemical potential of scale with mass density for each. A bulk force, which I'll come to in a second, and then an epsilon that sits in the momentum, which we tend to call entrainment. And so the entrainment has one job, and it is to tell us how easy it is for one of these fluids to move relative to the other. Okay? And there's a lot of discussion as to what that should be, what the number should be, but especially in the neutron star crust.
But if you include the electron fluid,
yes,
then the entrainment is more complicated because you have protons, neutrons, and electrons. Comment on that?
I don't know.
You don't know. Okay.
No, I don't know. I think the standard picture is this. Whether you need to go further, I don't know. But for example, you can show that the equations that we're using are equivalent to the two-fluid model in helium, say, with normal fluid and thermal excitations. If you think of the entrainment with entropy, so the heat, as giving the entropy component an effective mass, then these are exactly the same systems.
And another question.
Yeah.
You put the magnetic field here. The electrons, what do you couple to the spins to?
Yeah, those are very good questions, and I don't know. So this is the Newtonian version of the two-fluid system. I could have given you the full four-fluid system in general relativity. I just decided not to do that. That would have electromagnetism and heat flow and things in it. So those equations exist, but I think it's fair to say we don't really know what the parameters should be to go into them, okay? Because remember, the great advantages of fluid dynamics is a phenomenological theory with a bunch of parameters that we call pressure and so on. Here, there's an extra parameter that we call entrainment. The fact that we have a couple of parameters, depending on how many, so the entrainment is a matrix, I guess. If you take all the different options, all the different fluids, species into account, we really don't know how many of these parameters we need, and we really don't know exactly what all the values should be. Okay, so I think the real question is, or the difficult question is, we want to build a model that's as realistic as we can manage to work with. Okay, and then the question is kind of different. You say, okay, so you can think of many different phenomena I should take into account from the small scale, right? Do they make a difference on the large fluid dynamic scale, yes or no? And I think, from my personal view, is that it's often very difficult to say. So we need to check if there is a new idea for something we should try to put into this model, we should put it in and see what it does, right? That's my view of it. Okay? So anyway, that's what goes into these models, but as we've said, electromagnetism could sit in this force. Another thing that sits in this force is the interaction between vortices and the matter and so on. So the other thing that typically goes in is some statement about a vortex mutual friction. The typical logic follows the work in helium from the 50s by Hall and Bynum, which I'm sure you heard about last week. The idea is you put in a resistivity that just says it costs you this much to move, say, a vortex relative to the charged fluid, say the electrons or something like that, doesn't really matter. And then you invert, and then that's balanced by a Magnus force acting on the vortex because of the flows. And then you invert this relation to get rid of the vortex velocity. That's the phenomenological calculation. And then that ends up being an average vorticity over here. So this now it's not irrotational anymore, and a force over here that people typically call mutual friction. Okay? That's how the logic goes. It's not clear, to me at least, that this logic works if you make the system more complicated so that the vortices can interact with more than one of the other species. This inversion doesn't work anymore. It's clear that it doesn't work so well if you account for tension in the flux tubes and the vortices. So there's a big problem here. Of course, the flip side is that if you don't do this, follow this strategy, you might have to deal with working, say, with a vortex type fluid or something like that, a vortex component, and that might not be what you want to do in the hydro model. But what you want to do and what you should do might not be the same, you know. So that's okay.
So one naive question is here, because it's my ignorance. This mutual friction is not dissipative, is it?
Yes.
But yes,
it is dissipative.
It is dissipative.
Yes.
Right. Okay. But entrainment it's not.
No, entrainment is not.
Okay.
That's right. Okay, so this is the type of model that people have been using to describe glitches in a nutshell, and the kind of models that we've been using to look at, say, neutron star oscillations and things like that. So the state-of-the-art models build on this kind of description.
Can I ask you this? Second term in mutual friction, is this or that before?
Sorry, this one?
Yes.
What about it?
Is this the or that before? Or this was? It's because you said that it is dissipative. It's not always mutual friction.
No, there's a piece that this piece is dissipative, this piece is not dissipative.
That's what I.
Yeah. But then there are different names for different pieces, if you like. So the typical story is that in the outer core of a neutron star, the main agent at play is vortices, electrons scattering off of the vortices. Think of the electrons, they can't sense in the individual vortex scale, because the electron mean free path is something like centimeters, say. Okay? So the electrons move as a fluid on a much larger scale, so they scatter off of magnetic fields that are introduced on the vortices by the fact that the protons form a superconductor, so they can sense this small vortex scale. So the protons are dragged along by the entrainment, forming a magnetic field on the vortex, and that magnetic field then scatters electrons. That's the usual story. Okay? Now, if you work out the numbers, that leads to this friction coefficient R being small. That means people usually drop this piece because R squared is small, and just look at this, it just becomes an R, and then work out what happens. Now, that might not be the right thing to do for a number of reasons. First of all, in the crust, it could be that the scattering, the main scattering is probably not off of the electrons, but off the nuclei, and that changes this picture. I'm not going to talk about that. It could be that in the core, actually, it's more frequent that the vortices scatter off of flux tubes, like in principle in some sort of idea of, say, grid turbulence, where you try to drag a vortex array through a set grid. Right? Imagine the flux tubes, which are much more plentiful than the vortices, try to drag a vortex through somehow this set. It could lead to essentially pinching off, forming little loops, and so on. And that could lead to this coefficient, effective coefficient being quite large. The problem is it becomes a velocity-dependent statement because it depends on how hard am I trying to push this vortex array through the flux tube. So what is the relative motion? And that makes the problem a bit nasty. And then the other thing to keep in mind is we know that this story comes from saying we're really only interested in a uniform kind of vortex array, a straight vortex array. And that goes back to the question from before, what are we assuming about the rotation? Well, we're assuming that we're trying to model uniform bulk rotation, more or less. And so that then we would have a linear vortex array, right? But we know also from the 1950s that this is not what vortices tend to do. Vortex motion tends to become turbulent quite easily, okay? And so the argument in the neutron star literature in this sense is quite interesting because for a long time you'll find many statements like, but the vortex tension is so enormous that there is no way that the vortices would do anything other than be as straight as they can possibly be. And then move on. But I think it's becoming clear that that's not necessarily the right thing to do. So the problem is, what should we do? And this is where it becomes much more sketchy, because the reality is there's been very, very little work on trying to understand what turbulence might actually do, so what vortex turbulence would actually do to neutron star physics. Okay? And I guess that's the point of this meeting in a sense. So usually, if you take the linear vortex array, it's easy to show that you get an exponential relaxation between these two components. It essentially introduces a timescale that's quite short. So the two fluids would couple on some tens of rotation periods of the system, which is much faster than any observed glitch type events, which basically tells you that if this standard story has anything to do with reality, then the mutual friction coupling is only involved in the initial sort of glitch rise phase where the angular momentum is transferred. It has very little to do with how the system relaxes after.
Can I say something? It seems to me that the comment that I can make in this type of modeling that you have here is that because when it comes to the components that you have, you basically practice assume that the vorticity in superfluid is a continuous. And not only that, but you also assume that it has this solid body rotation alignment with the rotation axis. So it seems to me that some very important questions, like the ones that you mentioned, as is, for example, what would be, for example, the relation between the elastic tension and, let's say, some inertial effects that come up from the main fluid, they are basically outside the reach of this model. It seems to me that this is a model which already puts you in some kind of way of thinking for which you cannot escape unless you actually take into account what the vortices are.
No,
just a comment.
No, but this is absolutely correct. But what I'm trying to describe to you what people are doing, not what people should be doing. That's the difference. And the bottom line is that that kind of comment is exactly why more people that work on the neutron star models should talk to people that work on the smaller scale physics, okay, or on lab systems. There's absolutely no doubt about this whatsoever. But what I'm also doing is I'm trying to paint the simplest possible picture. There has been efforts to do a few other things, so that's what I'm going to mention, okay?
What I can say is that you might be right like that. I think what is the key question, the question that actually can make a difference here is whether you have instability in your system. If you have instability, I think you need to move away from this picture here. That's the difference for that.
Yeah, and that is a nice lead into the next slide. So the bottom line is, if you go to the lab systems, we know that this story is not right. We know the story is not right for different reasons, like I mentioned, tension and inertial effects and so on. But we also know it's not right because straight vortex arrays tend to be unstable. And so the famous example of this instability is called the Donnelly-Glubberson instability. It's essentially you have a vortex array like this, and there's a flow in the other component introduced along this array. Okay? That tends to trigger turbulence. So this is just some pictures for you. And that means that the vortices are tangled up, forming little loops and so on, and with an energy spectrum that looks a little bit like classical turbulence, which I'm sure you saw last week. Now, the key question from the neutron star point of view is not, does this happen, but what can I possibly do to model it in a fluid dynamics kind of picture? Because this is where there's been a huge amount of work, in particular for superfluid helium, on simulating vortex arrays, line by line, modeling the interactions and intersections and the forming of loops and so on. Okay? But remember, I'm trying to describe a 10-kilometer object. And keep in mind when I say 10-kilometer object that the highest resolution numerical simulations people are able to do for neutron stars, for say neutron star mergers, which is one system where you would expect all sorts of complicated dynamics, is about 100-meter resolution. Okay, that's the best that we can afford to do. Okay, so let's not kid ourselves and say I'm going to resolve this with some, exquisite precision. That's not going to happen. Right? And so we need to know what should we.
Not too big, you see, because 100 meters, 10 kilometers means 100 lattice points roughly in one dimension. That's 100 kilometers.
That's correct, but the vortices are 100 Fermi.
No, I understand.
And so if I want to average, so I'm just saying that when I take this kind of thing, okay, a line
probably can go close to 1 meter. 10 meters.
Yep, maybe. So if you take a vortex line simulation, then you have to do, there's a leap of faith. I'm sure Bryn showed his fanciful simulations last week, where you have sort of 1,000, 10,000 vortices, right? There's still a leap of faith as to saying the dynamics here scales up somehow to 10 kilometers. And the problem, I think, is that with the line simulations, what we're actually doing is we're effectively simulating what one could call one fluid element in the sort of fluid model. And I think that's, so we shouldn't say, here's the hydro, and then I scaled that phenomenon up to 10 kilometers. It's saying, this is what should go into my averaged hydro model. And then we can talk. I think that's where we should be.
And we have to know at what scale you can get from vortices to hydro.
That's right. And I think again, that's a bit sketchy, right?
Can I say, that is the kind of things that we discussed last week. In fact, what you say, I fully agree with that. At least in the helium for community, because we realize exactly this problem, we have developed the mesoscopic model, which actually, and we try to connect the mesoscopic picture with the macroscopic picture. So the answer is that you need a better macroscopic model without resolving the individual models.
That's correct. That's correct. And so what And that's the essence of where I'm going, right? I'm trying to say our models are always going to include more because we need the electromagnetism and so on, but there will be an overlap with what is being done for, say, helium, right? Where we can try to import some of the experience that you guys have, right? And I think that's, at least we should ask ourselves where it would come into play. Okay? So the simplistic story is that if you do this, then the mutual friction has a different form. Basically, it scales, it becomes non-linear in the relative velocity between the two components in two-component model. Now, that is causing a lot of trouble if you want to do neutron star phenomenology for two reasons. One, it's a non-linear effect, so you need simulations. The relaxation is no longer local, it's no longer global as it was in the rectilinear vortex array, it's local. And that means that saying anything about vortex or turbulence and, say, pulsar glitches is a problem. It becomes messy. Okay? And that's why there's been very little work in that direction. Okay? The other thing is that much of what we do in neutron star astrophysics modeling is built on perturbation theory. We're looking at oscillations and dynamics of oscillations, which is a linearized model. But this is a non-linear friction. Okay? There is, I think, on the market for neutron star oscillations, only 1 or 2 papers that ever looked at what happens if you got a background relative flow so that you could actually conceivably do this. Okay? So this is beyond the scope of pretty much every single piece of work on neutron star dynamics. Okay? And that's why there's very little work in this direction. So there's been some effort. I think maybe the most kind of impressive in a sense are the simulations that were done in the Melatos group in Melbourne by Carlos Peralta in his PhD thesis, where they looked at just using the standard two fluid equations from helium, what happens if you switch on and off or switch between these two, the linear friction and the turbulent friction. So those simulations were really nice, and then they were not pursued particularly. They were nice because they demonstrated how one could take this further, but they were problematic because the switching between the two kinds of friction was done by hand. So you set up the system, switch on to the other friction and see what happens, or set up the system and switch back and see what happens. So that's a nice sort of toy thing, but it's not what happens in reality. In reality, you should switch between one friction to the turbulent one locally, depending on whether the instability is active or not. Okay? And that has never been done, I believe, for neutron stars. Okay?
So I have a question about this instability. What is known about this instability in lab systems? If we try to mimic, the main difference between lab system and neutron stars is you have a lot of other excitations in the neutron star. Right? You have electrons and the protons are normal, you have protons. Is this instability robust when you have other ways to dissipate energy?
Has it been done, has anyone looked at how this instability works for neutron star systems?
Right.
With neutron star,
and you throw in some quasi-particles in a mixture.
So I don't know the answer to that question. I was going to talk a little bit about what has been done to try to do this in situations relevant for neutron stars. It's not enough and not a lot, but at least there's been some things. So we can maybe talk about that later. I think that's a very good point to ask for discussions later in the week, because there's something that's a direction where I think one could actually do some useful, actual work. Okay. So one of the problems is that the switching between straight vortex array and turbulence is not what we want. Okay. And the reason is very simple. In the total, completely turbulent vortex system, you have no bulk rotation. Whereas neutron stars don't suddenly cease to spin when the vortices would become turbulent. So you need to look at polarized turbulence. And that's, even in helium, is much less explored than the sort of total turbulent system. And that means that some of the systems, the models that people look for in the lab, like the grid turbulence, where you have a grid and you push the vortices through it, are not necessarily relevant to us. So we need to keep that in mind. Okay, and the argument is quite simple. The array, if you put in rotation in bulk rotation in the flow, the vortex array is stabilized by this, and then it would be destabilized by a relative flow. So in principle, you'd expect some switching between these two at some critical rotation rate. So here's from a paper by my student Trent Sidery some years ago, where we just looked at the two models and some experiments that people have done in helium, just to see how one could just ad hoc put these two forces together and ask, what difference would it make? And so this transition, I think, modeling polarized turbulence is where we need to go for neutron stars, but I don't really know how to do that at the moment.
Can I say something? Because I see a little bit of dangerous confusion here. Because if you start with a macroscopic equation like the HBBK equations, nothing stops you to use this equation after the stability, and it will produce the you turbulent states, no problem. Such calculations have been done, like for example, when this equation has been used to tailor wet flows. They have rotation and they have turbulence. I think your problem is the way that I see it. It's not so much that, but the problem is whether you can trust the HBBK equation once you move away from the order lattice. That is the key problem. There's no problem in solving it.
You're right. So I'm not talking about solving the problem. I'm talking about, is that description actually the description that you should be using? I'm saying exactly the same thing as you.
If it becomes turbulent, I would say no.
Exactly. So I'm thinking what you need is a different description.
Yeah.
Okay.
That's fine.
So the bottom line is, what you need is a fluid model that accounts for averaging over vortices, where there is in each fluid element, is a net amount of vortex length, say, that you're not seeing on the polarized rotation scale. Okay.
Okay.
That's what I would like to see.
Oh.
Okay.
So, sorry, may I also ask
Yes.
a little naive probably. So do I understand correctly that if one has this kind of model where one has this turbulent fluid probably connected to non-trivial part for higher momentum, is it correct that then the instability is kind of not inside there? So basically, the instability is only the way how to see that there should be several parts in this fluid, or should these equations also have those unstable modes, and one should see the instability? So
I don't know. I don't know. I think, again, that's an interesting question. I think that we're skirting very close to where I've ever gone with this, and probably a little bit beyond. But I think that there are some real questions as to what, as Sanjay said, what is the role of this kind of instability in neutron stars? How would it actually work when you got the other extra components? I don't know the answer. But I think that's something one could work on. I don't know how to do the averaging of a polarized kind of turbulent state, and I don't know exactly how it's done in the helium models, because I haven't really followed that up. I think there's something one could build better neutron star models that way. Right? I don't know. Okay, but that's maybe why we're here. So, okay, let me. Yeah. Oh, sorry. The L is a measure of the vortex length. If you just measure how much vortex length do I have in a fluid element, right? Imagine if you got a straight array, you just measure how long is how tall is the box, right? Whereas if you tangle it up, there's more, like a ball of yarn in each piece, so you can have more than just that length.
Plateau means we have just
So the cutoff here means that we've got, this is a rectilinear vortex array with some rotation. Here you got more vortex length per unit volume. Okay, that's essentially it. Okay, so what has been done in asking when would this instability appear in neutron stars? I think there's been a few papers on that, so I'm just going to talk about the ones that came out of our group. The first one was on free precession that I mentioned, and the logic is this: if you got a superfluid neutron star, and you have the crust, and you introduce free precession. So there's a wobble motion. Okay, the free precession is a fluid mode, if you like, of the system, and that fluid will lead to a circulation in the core that will lead to some flow along the vortex array. And that suggests that if you look at the neutron star precession as a hydro problem, then you should see this instability in the hydrodynamics. Okay, that's the logic. And so we did that, and we did that because there was a discussion about what would happen if you had a very strong neutral friction where flux tubes and vortices had to intersect. That's why we did this. And indeed, you find that.
So if they intersect, what happens?
So if they intersect, basically, if a flux, so you have a magnetized vortex, and you have a flux tube, a magnetic flux tube. The cost of cutting through is higher if they come at an angle. It's cheapest to cut through orthogonally. And that means that if you want to have this cutting through, they have to bend and then cut through. And that costs you energy. So it's a very dissipative process. Yeah, so that's the simplistic picture. Okay, whether that's true or not is a different story. But I think, again, that's something that's actually open to line simulations. If you can do magnetized lines, ask how would they move through one another. Okay. So here's a picture. It doesn't really show anything because I'm not sure how to explain it anymore. It's an old picture from our paper. But what it shows is that there is a range of wavelengths of modes in the precessing star that are unstable in the sense that the instability grows faster than the precession period for essentially this strong coupling regime. And that suggests that this idea that you get an instability of the vortices associated with this precession motion is brought out, okay, from the hydro model. Whether that's important or not is a different story, but it shows that we should worry about these instabilities being present in neutron stars, okay? The second model comes from neutron star oscillations, and it's based on one of the few papers that look at what happens if you go a relative background flow and then do perturbations. So we have a relative background flow, typical magnitude that one would need to explain glitches, and then we look at what happens to the simplest, or one of the simplest neutron star oscillation modes, which is called the R mode for Rossby waves, and it's essentially something that just takes the fluid and shears it like this on spherical shells. Okay? And then what happens here as well is when you put in the mutual friction in this model, the mutual friction is key to this instability operating, then you find that short wavelength modes in this system are unstable, pretty much as you would predict from this Donnelly-Gloverson argument. Okay? And so in order to market this idea, I guess, what we did was we looked at what happens if you crank up the relative flow, relative rotation between the neutrons and protons, and we found that you could predict the instability setting in for a given temperature, which kind of goes into the friction and rotation period, and then we just plotted this, and we compared somehow, you know, not necessarily very seriously, but anyway, we compared that instability, the critical onset for this instability, with the typical lag you need to explain certain glitch events. Okay, so the idea was, let's see if it could be that this typical fluid motion has an instability that's triggered by a relative rotation. Does that tally with saying that there is some instability in the system that basically leads to the vortices becoming turbulent or something, and then transferring angular momentum by magic or something, by some mechanism that we didn't try to explain. Okay? So this is quite naive. There was a follow-up to this where the calculation was done in more detail, which explores how the instability sets in and so on, but I'm not going to show you that. So these are the two of the few attempts to model this kind of thing for neutron stars. Okay, taking the fluid models as a starting point, which is not necessarily the right thing to do, but that's what we have sort of available to us. Okay, and I guess that's more or less the end for me, because I don't have anything else to say about it. It's not a main driver. People are not going in this direction because it's hard, right? And you know, we also don't really know whether the hydro that we're using is the right description, and we don't know what the parameters should be. So it's kind of a little bit of, we need to focus this and think about how we do these problems. The technology kind of exists, but I think, you know, we're not maybe not pushing it as hard as we could. And so that's me. I think the key point is, we know superfluidity, superconductivity is important for neutron star astrophysics. There's bunches of phenomenology that we don't understand, where we think we need to worry about these phases. That much is clear. There's very intuitive thing to argue that vortex turbulence, or indeed flux tube turbulence in some sense, could have decisive impact on these kinds of things. But the big question is, how do we, from the neutron star side, how do we learn from what is done on the smaller scale in lab systems, and, you know, where the technology is developed to a much higher level than what we've got? How do we learn from that and to take the next kind of step? I think that's where I'm going to stop.
So, simple question. You consider only precession but not mutation. Why not?
No reason.
Okay.
No reason. I was, you know,
Okay.
there was at that point in time a discussion as to whether the strong coupling between vortices and flux tubes should lead to fast period precession. So precession at the sort of time scale of the rotation period. And what the calculation we did demonstrates is that that kind of motion would be generically unstable. But it didn't go beyond that. And then there's also been another question which is related, that if you have that fast period precession, which you might think could be generic in these systems, how do you go about looking for that in, say, radio pulsar data, where when people do pulsar timing, they stack up a number of pulses, right? So to actually detect precession on the same timescale would be quite hard. And so that might become possible with, say, the square kilometer array in the 2020s, but at the moment it is not.
And another related question. What about rotation and these instabilities can lead to surface modes of the neutron star that can affect all this motion as well?
Okay, so in a neutron star, I think, so we don't think, the terminology is similar but a little bit different. So the surface mode, there are no surface modes as such in a neutron star. They're all global in some shape or form. But it definitely is the case that the instability will affect or trigger, or could trigger, oscillations of the star. Right? Some of those oscillations are more predominantly localized in the observatory regions, some of them are deeper, but yeah, so that's a very interesting kind of question. Also, the other side is, how would an instability affect a predicted oscillation of the star?
No, but what I mean, sir, what I mean, what of that type which can modify the shape. See, so you can have mass transfer, you see, from the equator, you see, towards.
Oh, no, that's right. That's right. That's right. That's right.
You have
that's right. So
three moments.
no, that's right. So we are, those kind of questions are very, very important for neutron stars for a number of reasons. For example, one of them is a variant of this is in a binary system where the tidal interaction impacts on the shape of the body, but also if you have what you call surface mode, what we call fundamental modes of oscillation, if they become near resonant with the orbit, then that can have a very, very large effect. And so that's something that is now being incorporated in, say, the LIGO search algorithms, is this near resonance. But if what is not known is what impact the state of matter would have on that kind of resonance. Okay, that's on the to-do list for several people, I think, but it's a hard problem.
Thank you.
What happens when the protons are normal to these restrictions?
Should be gone. Well, no, it should not be gone, but you can, if you have normal protons, you cannot make the argument that the vortices are magnetized. Okay, the vortices would then scatter off of predominantly the protons because they're bigger targets, or the electrons because they move faster. It's up to you. Right? But yeah, so then the friction would change, would drop, I guess.
People know it would because it would be much larger, more neutron vortex, and strongly coupled to the protons. I would just say it dissipates more effectively. Is this something that
I don't think that's the argument. So this calculation has been done, right, Bren?
Yeah, so there are calculations. I can't remember the numbers, but in general, the protons are superconducting, and you get this.
No, but it's the usual. It's the usual. But Vanessa, you might know. Do you remember?
Yeah. So you can so if you don't have normal protons, some scatter of the excitations that you get normal excitation, and that's a lot weaker. But there's also super density depending where you sit. So you can get to something like 10 to the minus 9, if I remember correctly. That's the average, but the one that you talked about is 10 to the minus 4. You have 5 orders of magnitude weaker if you do that thermal excitation system. Like a 5 or 1
you should explain that?
Yeah.
No, I think it's an important question. These coming, the what ifs, and the bottom line is for neutron stars, there's so many options that are not explored, right? And we tend to take things for granted. We tend to take, as I said, the two-fluid model as given, and then not worry about anything else. I'm just trying to put it in your minds that that's probably not something that should be given, but something that we need to continue to develop and improve. That's the main point.
Actually, I have one question. So with the nonlinear term that you added, do you get the same instability in the hydrodynamic equations as you get in the microscopic model, or?
That's an awfully involved question in reality, because I think phenomenologically similar behavior. I wouldn't put my hand on saying it's the same. That's too strong. Okay.
So you said concerning the intersection between flux tubes and vortices. So the fact that they cut perpendicularly, most likely this is qualitative results, or this is some kind of quantitative?
It's a phenomenological statement. So there's not been enough work on this in any shape or form. Okay, the argument is just saying, how much does it cost me to take a magnetic flux tube and cut another magnetic flux tube with a different magnetic field, and the overlap in magnetic energy is just smallest if you do it like that.
So by the way, what's the size of the flux tube as compared?
Same as a vortex, give or take, yeah. So that's something that I think, we've had discussions with, say, Carlo Berengi's group in Newcastle about asking, if you could do magnetized vortex line simulations with different populations, one that you could call flux tubes and one that you call vortices, because they've got slightly different magnetic field strengths, and simply ask what happens to these kinds of intersections. That's something I think is within reach of being done, right? And so that would help us answer some of these questions. How dissipative is that kind of system, right? Which we don't, I think, to be fair, we don't really know. It's maybe too simplistic.
Just a comment on the question. So I think that what you presented, it showed an understanding of some issues that I would like also that would have been the case also in more microscopic community. So I'm happy with what you said. My suggestion is that if you, in order to approach these problems of interest to you, that the vortices is not so much, I would say, the basic thing. I believe that your starting point should be what happens to the normal fluid, because our studies show that vortices they just pushed around by the normal fluid. So the most important thing is you start with what the normal fluid does. Then you can find out what the superfluid vortices do. Then you can use your
Okay. I think, but it's important. I think there is an important difference, okay? And that is that in the neutron star context, people don't tend to talk about normal and superfluid components simply because they always assume that they're far below the transition, and so there are no normal neutrons around. Now, so I think that statement is not correct, right? But I think that's the reason why people don't tend to think about this. But I think that again, that's might be a misinterpretation. Oh, because you got different fluid components. I got neutrons, protons, and electrons that can communicate with one another. It's a very different kind of system from the from helium.
Flow of another superfluid.
Yeah. Protons.
But then how this can be called initial friction? Initial friction is between the normal fluid and the
Oh, by analogy.
All right, so that's how you got the.
No, sorry, by analogy. No, that's right.
There cannot be friction between two superfluids because they
No,
don't
no.
have any friction.
No. Let me go over that again because it's important. Okay. The neutron star story goes like this. I have a neutron vortex. Okay. It lives together with a proton superconductor. The proton superconductor and an electron gas. Okay? The electron gas has a long mean free path, centimeters, say. Okay? The vortex is 100 Fermi. The proton superconductor can sense and react on that scale because it is a superconductor, because of the coherence length being about the same. Okay? And so the strong interaction induces the flow, because of this entrainment, of protons around the vortex. The vortex is now magnetic. Okay? That magnetic vortex scatters electrons on the larger scale. That gives you the friction. It's a very different physics mechanism to the I'm scattering thermal excitations in helium. Okay? The mathematics is exactly the same. That's why it's called mutual friction.
What about the physical parameters?
Oh, completely different. Oh, completely different. Oh no, but it's adapting the language to different parameters. And one of the big questions is, what are the parameters and what else is important? Right?
Okay, I think maybe we can continue the discussion in the afternoon. So thanks a lot.